In today's note, we're going to be looking at normal distributions and z-scores. So we've talked about z-scores before, but we're going to be looking at how we can use them to help us determine the area or probability underneath a curve. So first we want to look at the normal distribution, or what is a normal curve. We've talked about this in the last note. It's also known as the bell curve. But what a normal distribution is a continuous probability distribution where data are distributed symmetrically and unimodally about the mean. So the key thing is symmetrically, so it's the same on both sides of the mean, and unimodally because there's the one mode. We've talked about frequent examples such as height, weight, or IQ, and it's one of the most common types of distributions that you will see. So there are some properties of the normal distribution. It is symmetric about the mean. So we've just mentioned this, how it's symmetrical on both sides. 68% of the data will be found within one standard deviation. 95% of the data will be found within two standard deviations. And 99.7% of the data will be found within three standard deviations. So the key thing here is just how or what percentage of data is found within each standard deviation. Again, we want to remember that the area under the curve is equal to 1, because again, that is our total probability. So again, we can see from the mean in the middle, or we could say 0, and we have the mean plus 1 standard deviation, and the mean minus 1 standard deviation. So again, this whole section, so within one standard deviation, we have 68%, roughly. Then if we look at, again, at two standard deviations, so -2, or so 2 below and 2 above, if we look at those, two standard deviations away, we have our 95% of our data, and then finally 3 standard deviations away, we have 99.7% of our data, and then the rest is on the outskirts. So again, that's just going to be helpful to know because we know what percentage of data is underneath. So for example, in example 1, the grades in a math class are normally distributed and they have a mean of 64% and a standard deviation of 12%. The grades in a science class are also normally distributed and have a mean of 64% and a standard deviation of 6%. What is the probability that someone scores greater than 76% in math? So if I'm going to roughly look at my normal distribution, which I can see just kind of roughly drawn here, I know that in my middle or my mean, I have my mark of 64%. And if I look within one standard deviation in either direction, so that's one standard deviation, or plus 6, or if I'm looking at math, plus 12%, so I am at 76%. And if I look at one standard deviation below, that's 64 minus 12, so I'm at 52%, or minus 1 standard deviation. So what I want to find is the probability that someone scores greater than 76%. So I see that 76% is exactly one standard deviation. So what I want to find is the area underneath the curve in this section. So I need to figure out what percentage that is, or what that area underneath the curve is. Well, I can use a couple things to help me figure this out. If I'm trying to find the probability that x is greater than 76%. Trying to find the area underneath the curve. Again, I know that 50% of the data is in this direction, 50% of the data is below the mean, because again, the mean is in the middle. I also know that within one standard deviation, so in there's 34% of the data, and here there's 34% of the data as well. So I basically want to find everything that is greater than the 76, so everything that's in the green. So what I'm looking at is I want to find 50% minus 34%. I know that everything in the upper half above the mean is 50% of the data. I know that 34% of the data is contained within the one standard deviation. So if I do 50% minus 34%, I should find out that it's 16%. So that means that everything in green, or everything above scoring 76% on the test, works out to be 16% of the data, or the probability of 16%. So therefore, 16% of students score higher than 76%, because that's the area underneath the curve. If I look at B, what is the probability that someone scores between 52% and 70% in science? So again, I'm going to draw my normal distribution, just roughly drawing it. I know that I have my mean in the middle, which was 64, and I'm looking between 52 and 70%. I do know that my standard deviations, if I go one standard deviation above, again for science, the standard deviation is 6. So if I go one standard deviation above, I'm at 70. If I go one below, I am at 58. And if I go two below, so minus 2 standard deviations, I am at 52%. So looking at this, what I want to find is I want to find the probability between 52% and 70%. So I want to find everything in this shaded part here. That is what I want to find. So I'm trying to find the probability that x is between 52 and below 70. So what I can do is I know based on my normal distribution what percentages of data fall within certain standard deviations away from the mean. If I look at one standard deviation above, there's 34% of the data. One standard deviation below is another 34%. And lastly, the last bit of standard deviation works out to be, in total, it would be 34% plus 13.5%. So that means in total, I can add up all of these percentages below to find the probability of a score between 52% and 70%. So if I look at all my data or my numbers, 13.5 plus 34 plus 34 works out to be 81.5%. So that means that therefore there is an 81.5% chance of a mark between 52%, and 70%. So it's just using the idea of what standard deviations are and what percentages of data is between standard deviations underneath the graph. So notation that's used to describe a normal distribution is x approximate n, and then mu, comma, variance or standard deviation squared. Right? Again, the simple standard deviation squared just means variance. And x is just referring to the distribution of the data. So all this is saying is that the distribution is normal, and it tells us in brackets what our population mean is and what our standard deviation is, because those are the two things we need to use to help us figure out the percentages or probability. A standard normal curve is a special normal distribution with a mean of 0 and a standard deviation of 1. So you can write that as x approximate n with 0 and 1. So this area, or this normal distribution, the area underneath the curve can be found on page 480 and 481. So this will give you all the probabilities, certain standard deviations away from the mean. So you can use this if you get a standard deviation that is not nice, like 1 or 2 or 3. So this page would be used as a reference to tell us what the probability is. So what happens if you don't have a special standard deviation curve or special normal distribution curve? We can just transform or standardize the variables using z-scores. So we've talked about the z-scores before and how they tell us the number of standard deviations away from the mean. So we have the formula as z is equal to x minus the mean over standard deviation. So again, we have mu, or the mean, we have x, which is a specific value, and we have our standard deviation. So a positive z-score tells us numbers of standard deviations above the mean, and a negative tells us the number of standard deviations below the mean. Now, the key thing that we want to keep in mind is that if I have my normal distribution, I'll look at two examples. If I have my mean in the middle and I get an x value that is above, I am looking for a z-score. What the z-score tells me is that it gives the probability of getting x from the value and everything below. So it gives the probability to the left. So basically it tells you what is the probability of getting everything below. Which is similar to percentiles, where it tells you the percent of people or the probability of people that have your mark in every or less. The same thing, if I'm below the mean, my x value tells me everything, or the z-score gives me the values of, or the probability below or to the left of that value. So if I want to calculate the z-score for a normal distribution with a mean of 14 and a standard deviation of 4, I want to keep in mind that the z-score is equal to x value minus the mean divided by standard deviation. So if I look at x is equal to 11, so a data point of 11 with a mean, or with data that has a mean of 14 and a standard deviation of 4, basically what I want to find, if I draw my probability distribution, I want to find, again, if 14 is in the middle, I want to find what is the probability for the z-score of 11. So that means it would be here, and it would tell me everything below. So that's what I want. So if I find my z-score, z is equal to x minus the mean, so 11 minus 14, divided by the standard deviation, which is 4. And if I get, or do the calculation, I get negative 0.75. So this value is what you're going to use on the chart that we referenced on the last page, or on the last note, or sorry, section, the 480 and 481. So the way that it works is that you look for this first part, so the first decimal, the first two numbers, on the left side of the chart, and this last number you look for on the top of the chart. So you use the two to figure out where you are and to figure out what the probability is. So this is your z-score. So again, if we're looking at an example, if I have the middle value as 0, then this is negative 7.5 standard deviations away from the mean. So negative 0.75. So that's where everything tends to be. So if I use that chart and I find what is the value or probability or area underneath the curve for a z-score of negative 0.75, I should find, if I use the chart correctly, that the probability of having of the data value of 11 is 0.2266 or 22.66%. If I look at my next example with a data value of 21.5, so again, if I draw my normal distribution, I have my mean, my normal distribution, I have my mean in the middle, which is 14, and I'm looking for a score that is 21.5. So basically, again, I'm looking for everything underneath the curve. We're using a z-score to help me figure out the probability of finding or getting a mark of 21.5 or a value of 21.5. So basically, I'm using that z-score to find everything that is underneath the curve in this section. So this is what I want. I'm going to use my z-score formula again. So 21.5 minus 14, all divided by 4, which gives me a value of 1.875. But based on the chart, I'm going to round it to two decimal places. So 1.88 is my z-score. So that means that that data value of 21.5 is 1.88 standard deviations away or above the mean. I can use these numbers to go to my chart. So again, I'm looking at the left for 1.8, and I'm using 8 on the top to figure out what the probability is for this score, and I should find that the probability of 21.5 is equal to 0.9699 or 96.99%. So basically the probability of someone getting that score lower is 96.99%. Because again, the probability from the chart tells us everything from that value and below. So example 3, Melissa has 84% in data and her class marks are normally distributed with a mean of 74 and a standard deviation of 8. Carly has 83% and her class marks are normally distributed with a mean of 70 and a standard deviation of 9.8. Determine who should get the data management scholarship. So here we want to compare our two students and we want to see who has a better overall distribution of data. So we need to look at a z-score so we can see how far away from the mean are her values, or what is the standard deviation of her mark away from the mean. So again, the z-score is equal to x minus the mean divided by standard deviation. So if I look at Melissa, and I look at her normal distribution, in the middle it's 74, and she is at 84, which is over here. So if I look at a z-score for Melissa, z is equal to 84 minus 74 divided by 8, and I should get a z-score of 1.25. If I look at Carly, again, her class mark middle 70, and she's at 83. So if I find the z-score for Carly, the z-score is equal to 83 minus 70 divided by our standard deviation, which is 9.8. So our z-score is equal to 1.33. So looking at this, that means that Carly's therefore Carly has a higher z-score, so her data is farther away from the mean. So Carly has a higher z-score and should get the scholarship because she is farther away from the mean, so her data point or her score has less people, or has more people below it and less people above it. So she should get the scholarship. And if you wanted to look at it at a standardized one, or that special normal distribution that we talked about, so if we look at a mean of 0, we have Melissa at 1.25, and we have Carly at 1.33. So that means that Carly is above Melissa. She is farther away. Example 4, perch in the lake have a mean length of 20% and a standard deviation of 5 centimeters. Mean length of 20 centimeters and a standard deviation of 5 centimeters. Find the percent of the population that is less than or equal to the following lengths. So again, because we're looking for less than or equal to, we can use our z-scores to find out that difference or to find that probability underneath the curve. So again, if I look at my normal distribution, I have a mean of 20. In this case, I'm looking for 16, which is below, so I want to find everything that is from that line and below. I want to find that area, so I need to use my z-scores. So if I use my z-scores, I get 16 minus 20, or the value minus the mean, divided by the standard deviation, which is 5, and I should get negative 0.8. Once I find this z-score, I want to take this and go to the chart. So when I go to the chart, I should find that the probability of x being less than or equal to 16 should be equal to, or the value I should get is 0.2119. So therefore, 21% of the fish are likely to be less than 16, or sorry, not be less, are likely to be 16 centimeters or less. So that's how we can use probability distributions and the z-scores to help us determine a probability of a certain value. I can do the same thing with 28. Again, if I look at a normal distribution, 20 is in the middle, and I'm looking for 28%, 28 centimeters, so 28 is above, so I'm looking for the area underneath the curve from this section on. So again, I'm going to use my z-scores. So z is equal to 28 minus 20 divided by 5, which I get as 1.6. And when I go to the chart, I get that the probability that x is less than or equal to 28, I should get a value of 0.9452. So therefore, a 94.52% chance of catching a fish that is 28 centimeters or lower or less. If I look at 4 centimeters, again, same thing. 20 is my median, my mean, and I'm looking for something that is 4, so it's way down here at the end. So I'm trying to find the area of that small section. I use my z-score formula to find the z-score. So 4 minus 20 divided by 5, which equals negative 3.2. And if I go to my chart, I should realize that I can't find this value because the table only goes to negative 2.99, or basically 3 standard deviations above or below. So basically what it's saying is there's going to be such a small percent chance of this happening that it's insignificant, basically. Example 5, same idea, except now we're looking at intervals. So the results of a quiz are normally distributed, and they have a mean of 7 and a standard deviation of 2.2. We want to determine the percent of results that is within the given intervals. So if I look at A, I want to find what percent of results are going to be between 3 and 6. So if I look at my normal distribution here, I have my mean of 7. And if I look along, I want to find what percentage of the results will be between 3 and 6. So I want to find basically this area underneath the curve. So what I need to do is I need to find my 2 z-scores to help me figure this out. Again, remember that the z-scores always tell us everything that is below or to the left of our value. So first I'm going to find the z-score for 6. So 6 minus 7 divided by 2.2 equals negative 0.45. And the z-score for 3, so 3 minus 7 divided by 2.2 equals negative 1.82. So with these values now, I can go to the chart and I can find what is the probability of getting 6 or lower and getting 3 or lower. The probability of getting 6 or lower is 0.3264, or 32.64%. And for 3 or lower, it's 0.0344, or 3.4%. So now how do I use these two values to find out what percentage is between 3 and 6? Well, the probability that x is between 3 and 6 is equal to my value of 6, my upper value, so 0.3264, minus the lower one, 0.0344, because that difference would tell me what is between 3 and 6. So I get 0.292, so therefore 29.2% of the class is between 3 and 6. Now, in number B, or example, or part B, this is kind of different because what we're looking for is we're looking for a value that is greater than 5. So what is the probability, or what percent of results are going to be greater than 5? So we'll just look a little bit different notation. And if I draw my normal distribution, I have 7. I'm looking for 5, but instead of looking less than, I'm looking for greater. I'm trying to figure out what percentage of the values are greater than 5. So I'm looking for the area underneath the curve from 5 and above. So I need to use or find my z-score for 5. So 5 minus 7 divided by 2.2, and I get a value of negative 0.91. And if I go to my chart, I should find that there's a probability of 0.1814 or 18.14%. Now, what we want to keep in mind is that this value tells us less than 5, or less than or equal to 5, but I want greater than or equal to 5. So what I have to do is use my indirect method. So x is greater than 5 is going to be 1 minus the percentage that's below 5 or equal to or below 5, which I've just found out by going to my chart. So 1 minus 0.1814 and 0.8186. So therefore 81.9% will score greater than 5. So if we're looking for something greater, we have to use the indirect method and subtract it from 1, because our z-scores only tell us the probability for less than or below our value. Finally, in our last example, Jeremy's teacher congratulated him and told him he was in the 92nd percentile on this quiz. What did the teacher mean, and what was his mark on the quiz? So if I'm going to draw a normal distribution again, because that's what I've been focusing on, I know, again, my mean is 7. I don't know what his mark is, but I know the standard deviation is 2.2. But what I do know is that he's in the 92nd percentile, so that means his mark represents 92% of the data. Because we talked about percentiles, it meant that 92% of the class or of the population has the same mark or lower. So that means that he represents 92% of the students scoring the same mark or lower. Means 92% of the students scored the same mark or lower than Jeremy's. You could also argue that 8% of the class did better than Jeremy. So we want to figure out what his actual mark on the quiz is. So what we have to do, we are going to be using our z-score again. We've done something similar to this, right, when we're trying to figure out a mark that's so many standard deviations away. So again, my z-score formula, value minus the mean divided by the standard deviation. Now the thing here is we want to figure out our z-score, right? Or we're trying to figure out our data value of x. So in order to do that, I need to fill in all my other values, the mean and the standard deviation I get, and my z-score I can get from working backwards. So what I have to do is look for 92% or 0.92 in the chart. So I'm looking on the internal part of the chart because I'm trying to find 0.92 or that percent, and I should get a z-score of 1.41. So that's my z-score. Now I can take this and put this into my formula. So I have the 141 1.41, which is my z-score, is equal to x minus 7 divided by 2.2. If I go through and I solve this, 1.41 times 2.2 plus 7 is equal to the value, the data point. And when I go through, I should get, or find out, I get 10.12 is equal to x. Therefore, Jeremy's mark was 10. So the key thing that we're looking at in this note, I know it was a lot, the key thing that we're looking at is how can we use z-scores to determine the probability or the area underneath a curve. We're using the idea that z-scores represent standard deviations away from the mean, and we're using the chart on page 480 and 481 to determine what that probability is.